Good morning. I hope you all are doing well, and I hope you have a wonderful weekend. We're going to continue on talking today about buffers. And on Wednesday, we started our discussion of buffers. A buffer is essentially a weak acid with its conjugate base, or a weak base with its conjugate acid. And because they're both weak, they can coexist in the same solution at the same time. And you would never do this with like hydrochloric acid and sodium hydroxide. Strong acids, strong bases push reactions to the product side, so they get used up. But the weak acids and weak bases, they kind of hang out, especially if they're conjugates, and it's pretty chill. So a buffer, again, is just weak acid with a conjugate base, or a weak base with a conjugate acid. And we looked at something called the common ion effect to describe through ice tables why buffers are so resilient to pH. And you can absolutely do that. And then also on Wednesday, we talked about one of my favorite equations, the Henderson-Hasselbalch equation, which is a really nice way to calculate the pH of a buffer. And the Henderson-Hasselbalch equation is, if I can get my chart, it's pH equals pKa plus log, and then I'm just going to write base over acid here. And the base over acid is a ratio. So you can, like we've been doing in ice tables, use molarity over molarity. So the molarity of your conjugate base divided by the molarity of the weak acid. But you can also use moles. There's many different ways you can rearrange Henderson-Hasselbalch, and we'll talk about it. So then, at the end of Wednesday, we went through the example, which I'm just showing you the last slide here, on how we had a buffer with acetic acid and acetate at a relatively good concentration. And we figured out on Wednesday that the pH of the pure buffer was 4.68. And then we went through several slides where we added a single milliliter of 1 molar HCl. And that 1 milliliter of HCl, which is like nothing, doesn't look like anything, it dropped the pH from 7 to 3 in unbuffered water. But with this acetic acid acetate solution, the pH stayed the same. So we're starting to look at how to calculate pH changes in buffers upon adding strong acids and strong bases. And we'll talk a little bit more about Henderson-Hasselbalch here in a little bit. But before I go any farther, I just saw Natasha and Anthony here. I wanted to have a little quick promo that today at 11 a.m. in the Bob Scott room in the library, which is kind of when you walk in the library, it's towards the back on the right, kind of. But anyway, there's going to be a special Chem 223 study session, and if it works in your schedule, I encourage you to check it out. There's also going to be one Monday at 11 a.m. in the science conference room, not too far from my office and stuff. So any questions on any of this kind of stuff? Cool. The method we used to get this number right here is what I'm going to start informally referring to as double ice. And the reason I call it double ice is there's first a kind of an ice table where you you figure out the effect of the strong acid or strong base that you've added. And in this example, the strong acid, it took away some of the acetate, the base. So you can see that the acetate went from 0.6 to 0.599. And in the process of destroying some of the base, it created more of the weak acid. So the acetic acid concentration went from 0.7 to 0.701. So that 0.01 more here and 0.01 less here is the result of the HCl. And that was like the first ice table. Then we did a second ice table where acetic acid was the reactant, hydronium and acetate were the products. And again, we solved for X hydronium, and again, the minus X and plus X from Wednesday were very small, so we basically ignored them. And basically, hydronium then was the acid concentration times Ka divided by the base, and that got to 4.68. And also, when you're thinking about the effect of a buffer, there's basically two parts that affect the amount of acid or amount of bases present. And one of them is some kind of a ratio between the acid and the base, which is what this part is right here. And there's also a Ka. And you also see that in the Henderson-Hasselbalch equation. because the pH of the system, one of the parts is the pKa, which is essentially the Ka of the acid. And then there's also this ratio between the base and the acid, or the acid and the base, depending on how you set it up. So those are the two parts that go into creating an effective pH for your buffer system. So, any questions on this so far? Okay. At the end of Wednesday, we looked at another version of the Henderson-Hasselbalch, all right? And this version of the Henderson-Hasselbalch is kind of like one of the titration pH calculations we did, where if there was an excess of acid, you found out the leftover moles of acid and divided it by total volume. This version of the Henderson-Hasselbalch right here, which is also in the handout on buffers and Henderson-Hasselbalch, is a really nice way to very quickly find the pH of your buffer upon adding, in this case, strong acid, or as we'll see in a little bit, strong base. So if you look here, pH equals pKa, which again is based on your weak acid, plus log. Now remembering that base over acid here can be molarity or moles. In this version, you have to use moles, all right? So what we're doing here is we're adding a strong acid, HCl, to a buffer with a weak acid, acetic acid, and a weak base, acetate. The strong acid will lower the amount of base present. Acids and bases will react with each other. On the other hand, as the base is used up, more of the weak acid is created. Now numerically, all right, the moles of strong acid that are going to be removing the base will add the same number of moles of acetic acid. So it's like if I'm using up 0.1 moles of acetic acid, that means I'm going to be making 0.1 moles of acetate. This is the thing about conjugates. If you use up one, then the other one comes in. So in this problem, you need to figure out pKa minus log of Ka, and then you can use the moles and stuff. We have here a liter of this stuff, so it's 0.600 moles of the base and 0.70 moles of the acid. Moles per liter times 0.001 liters will give you the moles of strong acid. So you subtract it from the base and you add it to the acid. So via the HH version of this equation, you get a pH of 4.67, and that's very, 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 very close to 4.68. That doubtful digit is definitely a player. However, almost all the time in chemistry, this is an acceptable range of error. All right, and honestly, at this point, I would be more interested in my own techniques in the lab before I started worrying about it. The advantage of this version is it's much easier, all right? Instead of having to go through what I call a double ice, which means first you take out the strong acid or strong base, and then do a second ice for the Ka and pH, this one just allows you to plug it right in. You do have to use moles, all right? But otherwise, it's pretty chill. This is a handout in your companion, and it's online that talks more about this equation and also some stuff we'll see here in a little bit. And as if you had nothing else better to do, don't throw tomatoes at me, please, I beg of you. This would be a cool thing to check out, look over and stuff, make sure that you know kind of how it works. Yeah?
The equation for 4.74, now is that changing Ka to pKa?
That's right, exactly, man. If you go minus log of the Ka, and this is the Ka for the acetic acid, minus log of the Ka, then that gets the 4.74, you bet. And again, that would be like on the table and stuff. This wouldn't be something you'd have to memorize. Good questions, Abby. Other questions? So if you add strong acids to buffers, all right, and you need to figure out the pH change of your buffer, this mole way is honestly a really good way to do it. You've got to use moles, all right, but otherwise everything is pretty chill. In the actual HH equation, again, you can use moles over moles or molarity over molarity, but the way that this one's set up, you have to use moles. And there's also a corresponding one for adding a strong base, all right? So it's more than just about adding strong acids, the strong bases are added too. So in the one we just looked at, the acid takes away from the base, but as the conjugate base is used up, it makes more of the weak acid. So you can see here how the acid takes away from the base, but it adds to the weak acid. And this one down here is similar, all right? A strong base will lower your moles of weak acid. It's always about the opposites, all right? But as much of the weak acid that goes down, it's going to add to the conjugate base. So it's the opposite of this one, all right? And again, as long as you just use moles here and stuff, this is really cool. It'll keep you from doing the double ice kind of thing and stuff. But if you decide you want to use that, that's cool too. Any questions? Okay, so here's a good question. And it goes back to something very, very simple. I was going to say basic, but that's like too much humor on a Friday morning this early when my caffeine hasn't kicked in. So, I was going to say, anyway, if you add a small amount of a strong base, all right, the question is what's going to happen? So before we even look at these answers, if you add a base to anything, all right, doesn't matter what it is, do you think that pH is going to go down, up, or stay the same? Up, that's right. And I want to make that very clear and reiterate. If you add a base, any kind of base, all right, to some amount of sig figs, may not be appropriate for what we have, but to some amount, that pH is going to go up because bases make your pH go up. Conversely, acids, of course, would make it go down. So on this problem, your strong base will make the pH go up, all right? So right away, C, D, and E are all out of here because that would be appropriate for an acid, not for a base. But you'll see that there's two versions of increased pH, all right? And the first one is the pH due to the strong base, or do you think it's due more from the weak base of the buffer? What do you think? Buffer, well done. The strong base, all right, is what starts the party, but the pH change is not from the strong base. The weak acid essentially reacts with the strong base and they wipe each other out. But in the process of using some of the weak acid, the conjugate base is created more. So any pH increase you see is the result of that weak base part of the buffer. That's why when you add a strong acid or a strong base, you will still see the corresponding pH changes, but they're much more dilute, all right? And that's because you're looking at the weak system changing, not the strong system changing.
Question.
If you wanted to create a buffer, all right, usually when someone wants to do this, there's going to be some kind of desired pH. So let's say that George and I want to make a buffer with a pH of 4.30. Cool. Hydronium is equal to 10 to the minus pH. So if you go 10 to the minus 4.30, it comes out to be this number right here, 5.0 times 10 to the minus 5. So notice here that we have a pH and we have a hydronium. In the best world, you will have a hydronium approximately equal to Ka and or pH about equal to pKa. If you go back to the HH equation on the board here, pH equals pKa plus log base over acid. If you have a desired pH, then hopefully your pKa will be about the same, all right? You want them to be pretty close. The base over acid part is kind of like fine-tuning the engine, all right? So if your pH and pKa start about the same, which means that your hydronium and your Ka would be about the same, that's a good place, and then you fine-tune that base-acid ratio. So again, if you have a pH that you want at 4.30, and the hydronium is about this number, you'd want to pick a Ka pretty close to that number too, all right? And in this table of acids and bases, you can look up different acids with Kas about this number. So for example, if you had a 10 to the minus 10 and a 10 to the minus 4 Ka, you would absolutely try to pick the 10 to the minus 4. 10 to the minus 4 is closer to 10 to the minus 5. On the other hand, a lot of times when people do these systems the systems will actually be listed as pKa's, which is fine. pKa means that you want to have your desired pH close to the pKa. The closer it is, the less like fine-tuning and stuff you'll have to do. So let's say that we want this buffer, and we look in the stockroom, all right? And the stockroom, which always has not all the chemicals you need, of course. But anyway, we have these 3 buffer combinations available to us. So what this means is maybe we'd have a bottle of sodium hydrogen sulfate and a bottle of potassium sulfate. We don't really care about the sodiums and the potassiums, but we are interested in that hydrogen sulfate combination. That would be a buffer. And if you look up on the table for hydrogen sulfate, the Ka 1.2 times 10 to the minus 2, and then pKa minus log of this number would be 2.00. But we dig around the stockroom more, and we also find acetic acid acetate. So again, acetic acid is usually sold pure. This would be sold in like a sodium acetate, potassium acetate, something like that. And then we also have the very dangerous but still usable cyanic acid and cyanide combination. Anytime you deal with cyanide, of course, you want to be very careful. I would put full gloves on and stuff. No licking of your fingers, kids. But anyway, it is a viable buffer and stuff that you could use for making it. So looking at these Kas and these pKas, and knowing that this is what we want, which of those combinations do you think would be the best one to choose? Acetic acid acetate, that's right. 10 to the minus 5 here and 10 to the minus 5, those are pretty close to each other, all right? So this would be a good place to start. This one, 10 to the minus 2, would be too acidic. If pKa is about equal to your pH, then that would be a pH of 2, which is a lot more acidic than we'd like to have, about 4.3. This one right here would actually be too basic, all right? It would start off about pH of 9.4. That would be pretty basic. We'd want to pick this one right here. Honestly, this would be the safest probably of all of them too on a practical level, but this is paranoid chemist talking. Questions on that? So hydronium, which equals in this case then 5.0 10 to the minus 5, equals the acid concentration divided by the base concentration times 1.85. So we know now that Ka and our desired hydronium are close, which is cool. What we're going to do now is think about how we need to adjust the acid to base ratio, or base to acid, depending on how you set it up. What I would do in this sense is I would solve for the actual ratio. And the way it's set up right now, we're solving for the acid over base ratio. And to get this, I would divide both sides by 1.8 times 10 to the minus 5. So on this side, you'd have 5 10 to the minus 5 divided by 1.8 10 to the minus 5. That's a number that comes out to be 2.78. And what that tells you in this context is that your ratio of acid to base needs to be 2.78 to 1. So for example, if you put in 0.1 moles of sodium acetate, the base, you would need 2.78 times that number, or 2.78 times 0.1, 0.278 moles of acid. And that should get you to a pH of 4.30. So this is kind of a cool way and stuff then to see what's happening. You can usually kind of figure out just on a rough scale if you need to add more acid or base. Minus log of the Ka, this number is 4.74. And we want 4.30. 4.30 would be more acidic than 4.74. That's one way to kind of figure out that you should have more acid around than you have base. Any questions on that? Cool. Here's an example of a problem. We're putting 8.4 grams of sodium hydrogen carbonate in with 16 grams of sodium carbonate. So again, carbonate and hydrogen carbonate are the active ingredients of this buffer. This has more hydrogen, so that's going to be the acid, and of course this has less hydrogen, so that's going to be the base. And the reaction you can think about then, hydrogen carbonate plus water, making hydronium plus carbonate. And it might be interesting to know what the pH is.
To prepare our buffer solution, we first weigh our conjugate pair, 16.0 grams of sodium carbonate, the weak base. and 8.4 grams of sodium bicarbonate, the weak acid. We dissolve these solids in 100 milliliters of water. The final buffer solution has a volume of about 120 milliliters and a pH of 10.5.
So in this problem, if you wanted to get to this answer, hint, hint, good idea to practice. Anyway, all right. If you wanted to practice, what you'd have to do, obviously, is turn the grams into moles big time, all right? Because regardless of which system you use, you have to use moles over liter if you use ice tables or moles. So you'd have to do this. What else would you need to look up to solve a problem like this? Ka, the equilibrium constant, that's right. So you'd have to look up the Ka for hydrogen carbonate, all right, which is a number, I don't know what it is off the top of my head. You could do it two different ways, this problem, all right. You could do an ice table, all right. You'd figure out it said it was 100 milliliters if I remember right, it doesn't really matter. If you figured out the moles per liter, you could do the acid, it would be going down by X. This thing would have the initial concentration plus X, but really what you're after more than anything is hydronium. So you'd solve for hydronium minus log of hydronium. But I'm steering you towards the HH equation because I think it's easier. pKa would be minus log of the Ka, the number you look up. You don't have to use volume at all when it comes to HH. You just turn both of these into moles. Moles of the sodium carbonate on the top divided by moles of the sodium hydrogen carbonate on the bottom. See if you can get 10.5. Any questions on that? Cool. So buffers are really, really handy in biology. Of course, a lot of times they use them to keep their solutions pure. They're definitely useful in chemistry. The iron solution we used in the first lab was actually buffered, and we'll use buffers more next week too. There's lots of uses for buffers, but one way we can use buffers as well is in the titrations. And in this lab that we did this week, the weak acid plus strong base and the weak base plus strong acid, the pre-equivalence region was basically a modified Henderson-Hasselbalch. So this next thing we'll do is we're going to come back into talking about the titrations. And we talk about titrations because the real goal here of this whole lab, this whole section, is really just to be able to find the pH with any combination of acid and base. It might be a buffer, it might be a weak base plus strong acid, who knows, who cares. You'll be able to figure out what the pH is and the concentrations and all that kind of stuff. So let's go back in now. What we talked about the buffers, we can now really make sense of what all these different equations are. And like we saw in lab this week, there's 4 kinds of titrations we're going to look at, all right? The strong acid plus strong base, which is what we talked about in the lab intro there a lot. Strong base plus strong acid, which is very similar to strong acid, strong base. Weak acid plus strong base, so acetic acid plus sodium hydroxide, those kind of reactions. As well as weak base plus strong acid, so maybe like ammonia plus HCl. And up here, I have 4 things which are very helpful sometimes in identifying what kind of a system you have. If you have strong acids and strong bases reacting with each other, they're conjugates, like sodium from sodium hydroxide or chloride from HCl. All of those conjugates don't affect your pH at all. So strong acid plus strong base, as well as strong base plus strong acid, the equivalence point, the steep part of the S-curve, pH of 7. All right? If you have a strong acid, strong base plus strong acid, you should see a pH which is equal to 7. We don't say the same thing when you have a weak system. Because at equivalence, where these 2 parts are equal to each other, the weak acid has turned into a conjugate base. And base being the operative word, your equivalence point, that steep part, should be greater than 7. You'll have a basic pH. And conversely, weak base plus strong acid, if the moles are equal to each other, that weak base has turned into its conjugate acid, acid being the operative word, your pH should be less than 7. So when someone finds a brand new acid or a brand new base, and believe it or not, this happens a lot as people study like organisms and stuff, they'll find things in blood and all. It's amazing the number of acids and bases. Anyway, a very quick titration will quickly tell you if you have a weak acid or a weak base, or if it's going to be strong. You titrate with something strong, sodium hydroxide, hydrochloric acid, and if your pH at equivalence is acidic or basic, probably means you have a weak system. Anyway, like we saw in the lab too, these titrations, to make sense of them, they're split into regions. And the regions really are defined by the mole ratio between the two species. The first thing that's listed is what you're starting with, and the second thing listed is what you're titrating with, what you're slowly adding in. And the reason we went through buffers is because the last two on here, the pre-equivalence region, uses like a type of a buffer reaction. And so in lab this week I said, oh, just take it as a leap of faith for right now. Well, now we'll be able to actually make sense of where these equations are coming from, and you can go from there. Any questions so far about this whole area? When you're doing anything with strong acids and strong bases, they're so powerful, all right? Their Ks are so product favored that we assume that they go 100% to completion. They either use it up, or they either use up what they're trying to attack, or they're used up themselves. So when I say that they annihilate, that gets your attention, and I did like that Natalie Portman movie, but anyway, it was Annihilation. All right, cool book. All right, prop that on. Good, Hunter? Oh, respect, brother. Anyway, Hunter's already been on my good list. That's the first statement. Anyway, digressing, prop that back on. Annihilate means, there we go, K is very product favored. Oh, I love that book. All right, prop out really good. K just means that it's very, very product favored and stuff like that, and they always push to the opposite side. There we go. Sorry about that. Maybe not. Weak acids and bases, though, have that crazy conjugate effect, all right? It's kind of like that extra zip when you think the reaction's done and something comes back to, like, haunt you. Haunt is really a stupid word to use here. There's a pH effect once they're used up, and that's unexpected based on strong acids and strong bases. Strong acids and strong bases, you either know they're there or they're not there, but conjugates, sometimes you have to think about their alternative. The Ka and Kb, which you do have a table for, is really useful. However, if you're the first scientist to look at one of these, you have to figure out what the Ka and Kb is. And there's actually a really cool way to figure out Ka or Kb using what we're going to call half equivalence pH point. And it was in the lab, but I'm going to talk about it here more. If you are a scientist and stuff, this is a really cool way to figure out your Ka or Kb value. And we'll talk about that. Ka times Kb always equals Kw, and again for us doing things at room temperature, 10 to the minus 14. If any of you do research with human bodies, human systems, which is warmer, you may have to adjust the Kw. Some of the things we're talking about may have to be changed a little bit. But most of the time in regular science anyway, things are room temperature, so it's no problem. pK and pKb can also be really helpful, and remember that pK plus pKb equals 14. So if you have pKa, 14 minus pKa would give you pKb, and vice versa. Concentrations and volumes are really important. And on this lab, all right, unless you're plotting the volume of titrant, which should be in milliliters, everything else is liters, all right? So make sure you go from milliliters to liters. How many milliliters in a liter? 1,000. All right, you're sick of me saying that. I'm sorry I keep repeating it, but it's so important. So it'll say, what's the pH after 30 milliliters? Turn that 30 milliliters into liters before you do anything else, because you'll need it. Molarity, which is concentration, is moles per liter. All right, so that's why we're kind of hitting that hard. Okay, so what we'll do now is we'll look at the different regions and stuff and talk about them a little bit.
When a molecule of hydrogen chloride and a water molecule encounter each other, they react to form a hydronium ion, H3O+, and a chloride ion. When sodium hydroxide enters the solution, It splits into sodium and hydroxide ions. The hydroxide ion and the hydronium ion react readily with each other to form two molecules of water. Sodium and chloride ions are left in solution.
So this is the strong acid plus strong base titration. It's one of the 4 kinds. And remember that what's listed first is what you're starting with, and the second piece is what you're adding in slowly. So on a graph, on a titration graph, pH is going to be the y-axis, and the x-axis will be the volume of the titrant, which is usually milliliters. So in a problem like this, it's going to be volume of some kind of a strong base, sodium hydroxide, potassium hydroxide, whatever. And these graphs look something like an S, and you have to use your imagination. It's kind of a lame S, but they kind of have this kind of a curve to it, all right? And there's basically 4 important regions that are nice to know. The initial point is literally only at 0 milliliters, and that point has just strong acid. So you haven't added any of the titrant, any of the strong base yet. So your pH will reflect that strong acid. Then there's the equivalence point where the moles of strong acid and the moles of strong base are equal. And you'll be able to tell this is strong acid, strong base because of the pH. pH should be 7 if it's strong acid, strong base. Then there's the pre-equivalence and the post-equivalence, which just relate the moles of what you're adding to what you're starting with. In this case, remember that we're starting with a strong acid, so pre-equivalence means that you have more moles of strong acid than you have moles of strong base. And these pHs, as you can see, should be under 7 because, again, you have lots of strong acid. On the other hand, post-equivalence means now that you've added more moles of titrant than you started with. So in this case, you'd have more moles of strong base added than you had moles of strong acid to begin with. And again, notice your pHs here, they're all greater than 7. On all these kind of problems, all right, the pH should be gradually increasing or decreasing. You won't see like skipping up and down or anything like that. So when you're calculating numbers this week in lab, you should see your numbers continuously increasing or continuously decreasing. Here's a question. We've got a strong acid, strong base. We plop them together and stuff like that. Which one of these is correct? Which one do you think is right? C, that's right. I'm kind of repeating this stuff over and over, but I want to make sure we're all really clear. It doesn't matter the concentration. It doesn't matter anything else. Strong acid plus strong base, pH of 7. Okay? Cool. So, going back to the strong acid, strong base, again, there's 4 regions, all right? And I'm just going to put the equations up here, and these are the same equations from lab. Knowing how these work makes your life really easy. Initially, you have just a strong acid. So minus log concentration of strong acid would be a great way to do it. But you can see here there's lots of references to moles and volume. So I rewrote the initial one here to show you and stuff that it's minus log the moles of strong acid divided by the volume of strong acid. And you have all this information in this kind of problem automatically. It'll say, 30 milliliters of 0.1 molar HCl, something like that. Well, 0.1 is literally the concentration, and 0.03 times 0.1 would tell you what the moles are. Remember, volume's always going to be liters and stuff like that. If you figure out the moles and the volume, then you can go through and find pre-equivalence regions pretty readily, all right? And it's again, moles of strong acid, not the security agency in Washington. Anyway, moles of strong base, of course, and you always divide by total volume. And again, your volume needs to be in liters, so make sure you translate from one to the other. Now, the equivalence point will be a pH of 7, and that's a nice hallmark if you have the graph in front of you to tell what the thing is. Notice here how I have kind of a little line right there. At this point, the moles of strong acid and the moles of strong base are equal. So sometimes it is handy to know what the equivalence point volume is. If you know that, then all the volumes left of it, greater than 0, will be pre-equivalence. And of course, everything past the equivalence point volume, you'll use this equation down here for post-equivalence. And I'll show you kind of an example of how that works. Okay, so let's look at an example. We've got 0.1 molar HCl and 0.1 molar NaOH. And we want to know what the pH is of the initial solution, all right? So first of all, again, try and figure out what kind of a titration this is. Is HCl a strong or a weak acid? Strong, all right? 5 strong acids, 3 strong bases. Is sodium hydroxide strong base or a weak base? Strong base, good. This is going to be a strong acid plus strong base titration. The reason I can say that is we know right away the volume and the concentration of what we're starting with. And in this problem, it says we're titrating it with the sodium hydroxide. So sodium hydroxide is what we're going to add in slowly. And initially, we don't have any sodium hydroxide, so we don't have to worry about that. Here's a list of the other strong acids and the other strong bases, all right? The ones that I would like you to know. And again, they pop up once in a while, but they're all going to be the same thing. And again, conversely, if you run into an acid or a base and I don't say something, then you can automatically assume it to be weak. Okay. So in this point then, for a strong acid, minus log of hydronium, all of the HCl has turned into hydronium. So you could also write here, if you'd rather, minus log concentration of strong acid. And if you want even more flexibility, you could go minus log moles of HCl divided by volume of HCl. All of these are equivalent when it comes to a strong acid. So in this problem, we know the concentration already, so lazy chemistry kicked in. Minus log of that concentration is equal to the concentration of H3O, pH exactly 1 at this point. Okay. Now let's say that we've dropped in 45 milliliters of sodium hydroxide. Okay, so now we are no longer at the initial point because we've added some of the titrant. And the question is now, what region are we in? Now, because the concentrations are the same, and we started with 50 milliliters, you would probably make a good guess here that 45 milliliters would be under equivalence. Volume times concentration for the acid is going to be greater than volume times concentration for the base. But why I bring this up is because you should really check to see like which region you're in. So you want to really, to do this right, you want to compare the moles of HCl to the moles of NaOH. And again, when you have these molarities around, moles per liter, which was what molarity is, times liters of volume will give you the moles. So for the strong acid, 0.100 is the concentration of HCl, and we'll multiply that by 0.050 liters of HCl. So in this titration, we have 0.0050 moles of hydrochloric acid, the strong acid. We can do the same thing with the base, all right? Now the base is also 0.1 moles per liter, but we only have 45 milliliters, 45 divided by 1,000, 0.045. So in this problem, 0.0045 moles of sodium hydroxide is what we have. And to figure out the region, this is the best way. You literally compare the moles. And you can see here that the moles of strong acid are greater than the moles of strong base. So this is a pre-equivalence region in this titration. Is that cool? Questions? All right. So once you have these numbers, that's when you can plug in to the pre-equivalence titration calculation. What you're trying to do is you're basically trying to figure out how much leftover acid there is. The strong base, again, annihilates. I'm not going to get excited this time. Darn you, Hunter. Anyway, the strong base annihilates the acid as much as it can, but there is going to be a leftover amount because, again, moles of strong acid are greater than moles of strong base. So you're figuring out the leftover moles of strong acid. You do want to divide by the total volume in liters. And again, notice that comes from the strong acid and the strong base. pH 2.28. Okay. Okay. Now, it might be also cool to know what the pH is at equivalence, all right? And at this point, you're probably sick of me asking about equivalence, but I'm going to keep pumping it in. At equivalence, the moles of HCl and the moles of sodium hydroxide are equal. And because they're both so product favored, we have only sodium, chloride, and water. Sodium ions, chloride ions, and water. Now, sodium and chloride ions, we looked back in the last section, and these are ions that don't affect pH. Like if you added ammonium chloride, we did an example of that. The ammonium makes the pH get acidic, but the chloride just kind of sits there. So all of the conjugates of strong acids and strong bases, the sodium from sodium hydroxide, the chloride from hydrochloric acid, the nitrate from HNO3, and the potassium from potassium hydroxide, all of those do not affect pH. They just stay at 7. So the only thing that's going to happen here with the pH is water. That's why we would expect the pH to just be equal to 7. Now, this part right here is how to find that volume to reach equivalence. And what I've done here is the moles of hydrochloric acid, which we got from volume times concentration, 0.005. And at equivalence, the moles of HCl and sodium hydroxide are equal to each other. So you can see by stoichiometry, the moles of HCl on the bottom and the top cancel, got moles of sodium hydroxide. This number right here is the concentration of your sodium hydroxide. So you can see how if concentration is moles per liter, I have it listed here as liters per mole. The moles cancel out. The number that you calculate, 0.050, that's the volume of sodium hydroxide needed to get to equivalence. So what this means is that this equivalence point will be at 50 milliliters. And that's probably not too big of a deal to you guys because you do, the concentrations here are the same. So if 50 milliliters of acid was needed, we probably need 50 milliliters of base. But if you want to formalize it, if the concentrations are different, remember that equivalence means that the moles are equal. So if you know the moles of what you're starting with, you can essentially divide by the concentration of what you're adding to find that volume. Wonder what the pH is at 55 milliliters. All right, and of course that's kind of a silly question, but I want you to see that you can calculate the pH at any number, all right? So Serge does 0.12 milliliters and Justin does 10 liters. You can use all these techniques and stuff to find these numbers out, which I find empowering, but of course I'm a teacher. Anyway, so from before, you still have the same moles of strong acid, all right? That hasn't changed. 0.05 times this number gave you that number right there. But the difference now is in this post-equivalence region, your base moles are larger than your strong acid. So we won't use the minus log and some kind of concentration equation anymore. Now we're going to use the 14 plus log version because that's the easy way to find strong base. So just like with the strong acid, but now with the strong base, you want to find out the leftover moles, all right? You never want to have 0 or negative up here, as some of you found on your calculators, but you want to have something positive left over. So in this case, strong base moles minus strong acid will give you some positive number. Divide by the total volume. pH should be 11.68. You can also check yourself because if you're adding a strong base, your pH should be basic, larger than 7. Cool. So here's like a graph, all right, and you can put in the different points. So the initial point was pH of 1. At 45 milliliters, we saw the pH was 2.28. The equivalence point for all strong acid, strong base titrations should be at 7, and you can see how it's 50 milliliters. And then finally, at just a little bit more, your pH jumped to 11.68. So notice in the strong acid, strong base, this is a very sharp part, very, very steep, all right? And that's the function we'll see here of a strong acid. And just small amounts will create huge pH changes, which is kind of interesting. It's like you've exhausted the one strong component, and then the other strong component starts taking over. Cool. Now, the similar system is when you have a strong base plus strong acid. And there's a lot of similarities to the strong acid, strong base. And just to make sure we're clear here, with these kind of titrations, you're starting with a base and you're slowly adding in acid. So you can see, and if you use your imagination a little bit, this is kind of the inverse of what we saw before. It's starting basic, it's going more acidic as you add more and more HCl. But like before, you're going to have an equivalence point, which is pH of 7. Pre-equivalence means more, in this case, base than acid, and the pH should be basic. On the other hand, down here with the post-equivalence, now we have more moles of strong acid than we have moles of strong base. So the equations, like we talked about very briefly, look really similar in this region to what they did in the other one. The initial point now is the pH of a strong base, 14 plus log the concentration of the base, or if you want to be cool for later, you can calculate the moles and the volume. Again, make sure all your volumes are liters. Then at pre-equivalence, you have more base than you have acid. Moles of strong base are larger than acid. So again, figure out the leftover moles of base that are left, divide by the total volume. Your pH should be basic. Then at equivalence point, your pH goes to 7 because those strong acids and strong bases have knocked each other out. And finally, post-equivalence, figure out moles of leftover acid divided by total volume. You're good to go. And like we talked about in lab, the post-equivalence here is the same equation as the pre-equivalence in the strong acid, strong base. And likewise, pre-equivalence here is the same as the post-equivalence in the strong acid plus strong base. So these equations do repeat, all right? And I'm hoping you're starting to see the patterns. Any questions on this? Okay. The one we'll spend some time with now.
Hydroxide ion is a strong base. It can be consumed in the body with a weak acid, such as dihydrogen phosphate ion produced in the kidney. In the reaction, an H+ ion transfers from the acid to the hydroxide ion to form water and HPO4 2- ion, the weak conjugate base of the weak acid.
So this is an example of dihydrogen phosphate, all right? It's a weak acid. It reacts readily with strong base, here represented by just hydroxide. So again, the hydroxide could have come from lithium, potassium, or sodium hydroxide. It doesn't really matter. The hydroxide steals one of the hydrogens to make water, and you're left with the conjugate base, which in this case is hydrogen phosphate. So this would be a type of reaction you could see. You could also do like acetic acid and sodium hydroxide, any of the acids we've seen plus a strong base. And if you look at this graph just as a general, it looks kind of like the strong acid, strong base, kind of. It's got the S curve, but there's a lot more gradual part right in here, all right? And we're gonna see, maybe not today, but on Monday, we're gonna see that this region right in here is very much like a buffer. And buffers resist change to pH. So there's a region in here where the pH is very, very gradual. It doesn't change very much. And that's what I didn't talk about very much in lab this week, because I want to talk about buffers. But just like the other graphs though, there's 4 important regions. There's the initial point where only the weak acid is present. There's a pre-equivalence region now where the weak acid moles are larger than the strong base moles. There is a different kind of equivalence point here. At equivalence, the weak acid and the strong base moles are equal. They essentially wipe each other out. However, the weak acid is turned into its conjugate base, base being the operative word. Your equivalence point here will be basic. So if you have an unknown acid and you titrate it, you see the equivalence point, the steep part is larger than 7, you've got a weak acid. Finally, the post-equivalence is going to be very similar to what happens when you have excess of base, 14 plus log hydroxide. And also, we'll talk about this on Monday, but the half equivalence point is really important. The half equivalence pH equals pKa, and you can turn then your pH as a pKa into a Ka. It's really cool. Notice that if the equivalence point volume is 25 milliliters, half equivalence volume is literally half the volume. So if you have takes 25 milliliters to get to equivalence, half that number will be the volume to reach equivalence. All right, we'll do more of this on Monday. I've kind of run out of time. Have a wonderful weekend. Study session, 11 a.m., Bob's got room in the library if it works in your schedule. Cool.